Thank you very much for attending. I'll just summarize my poster, which will be about the Aharonov-Crasher effect, Hamiltonian, when we include the div-E term, which was usually missing when the standard treatment of the Aharonov and Crasher. Now, we know that in the original work of Aharonov and Crasher, they start with this Hamiltonian, but they can write this only when they omit that term. And this interaction is omitted. Now, once they do this, then the quantum phase, similar to the Aharonov-Bohm scalar particle phase, is obtained. So only when they omit this term, this is obtained. Now, Hagen has established the equivalence of spin 1/2 Aharonov-Bohm and Aharonov-Crasher effect, however, within the framework of a relativistic, that's 2 plus 1 dimensional model based on the Dirac equation. Now, he based his treatment on the fact that the AC and AB fields are dual, and he got this expression for the cross-section, which looks for polarized particles, which looks much like the Aharonov-Bohm cross-section for a spin 1/2 particle, except that we have the appearance of this beta, which comes from the dependence of the cross-section on n, which is where n is defined like, this well-known parameter alpha is just n plus delta. N is the integer part, and delta is the fraction. Hagen commented that it's important to keep the mu div E term in the 3D, three-dimensional, non-relativistic original AC Hamiltonian, because this is just the analog of the curl A term in the spin 1/2 theory. Now, what we want to know is that if we start from the onset with the div E term included, then and calculate the scattering amplitude of the Aharonov-Crasher Hamiltonian, what we'll get. And we also, in the Hagen's work, there was a dependence here of the cross-section, not only on n, but also on the sign of alpha. The origin of this dependence was unclear. And also compare the role played by the div E term in the AC Hamiltonian with that corresponding curl A term in the Aharonov-Bohm spin 1/2 Hamiltonian. So we just write down the scattering amplitude for the AC Hamiltonian plus the div E term. This is the standard amplitude that one gets for the original AC Hamiltonian, and these two contributions come when you include this div E term. These lead as a cross-section to the following result. This is exactly the same result derived by Hagen, starting from the 2 plus 1 dimensional Dirac equation, and it's exactly, it has this dependence on alpha and on n and on sine alpha. The new thing is that the origin of this dependence on alpha, on the sign of alpha, is clarified. It's simply because here this additional contribution to the original amplitude comes in when alpha is negative. That is, the interaction is attractive. For positive alpha, whether you include div E term or do not include it, you get the same result. So it has no effect, which is physically plausible. Now, the second thing that we show that whether the div E term is effective or not, included or excluded, the polarization dependence of the cross-section is the same. So whether you include it or don't include it, there is no change in the dependence of the polarization. The only thing is that this value of beta shifts by 1. So when div E term is included, just this value of beta shifts by 1. Now, interesting special cases can be reported. That is when alpha is only a fraction, so it takes place when n equals 0 in the alpha greater than 0, and equals -1 in the alpha less than 0 case. In this case, you have for delta equals 1/2. That is, alpha equals plus or minus 1/2, which is, the magic value of alpha. You get a cross-section which is the same, whether you include or exclude the div E term. Moreover, if you set the incident particles spin and the outcome, or detect the out particles spin in the same directions, but so that the spin has only a planar component, then in this case the cross-section is isotropic, and it doesn't depend on the angle. That's it. So for more details, please visit us on this talk. Thank you very much for listening.